Welcome to podcast 4.1. Please proceed.
This is all stuff you know. You can either calculate molarity or molality. We won't do that in AP at all. Mass by weight percent. So, 10 grams of solute in 90 grams of water is a 10% salt solution. That makes sense. Then you have this thing called mole fraction, and we haven't really done mole fraction, but mole fraction is just how many moles of whatever you're talking about divided by the total number of moles. And again, we're talking about a solution, so it would be, you could talk about the mole fraction of salt. The mole fraction of salt would be moles of salt divided by moles of water and moles of salt added together. You could also talk about the mole fraction of water. We don't normally do that. We normally talk about the concentration of solute, but you could describe the mole fraction of water, and that's actually what we're going to do most of the time. You need to look at this symbol right here. This symbol is the symbol for mole fraction. That's kind of a weird thing. It's an X, and I know what you're thinking. Where in the world did they get this? I don't know. But mole fraction is a fairly simple concept that will apply to vapor pressure. All right, I'm going to have y'all draw some pictures of this in class. This is something that we rarely talk about, but the idea is when you make a solution, what happens? Well, you've got to take all the solute molecules that are all piled together, and you have to separate them, right? You have to split them up. So if they're sugar molecules, you got to break them apart from each other. If they're salt molecules, you have to break them apart from each other. And breaking those molecules apart takes energy. You also have to break the solvent molecules apart. So if you're talking about alcohol, they have to be broken apart. If you're talking about water, those have to be broken apart. If you're talking about benzene, then you still have to break those molecules apart. So if you expand the solute and you expand the solvent, then the last step is just allowing them to come back together. So that allowing them to come back together is going to set up new bonds, and that will release energy. Well, this is an awful lot like what we talked about in chapter 8. You have to break the bonds of all the reactants and then let all the bonds of products form, and whether or not it's exothermic or endothermic is purely a function of, did it take more energy to break up all the bonds, or did it release more energy when it formed new bonds? Same concept here. To find the delta H of solution, you just add the three of them up, right? So the endothermic stages and the exothermic stages, you add them together, Hess's law, one more time, and then you can find the delta H. If delta H is positive, if it absorbs a whole lot of energy, then the solution won't form, just because it takes way too much energy to make that happen. So some things won't ever dissolve, mainly because the delta H of solution is too high. And you can see this. You put energy in, and then as the solute and solvent start to interact, bam, you make a solution. If the delta H of solution is small and positive, so it's not too big, it's positive, but it's not way too big, a solution will still form, because what does the universe want everything to do? Entropy, right? So you can talk about the delta G of a solution if you want to. Will it spontaneously dissolve or not? And it's that same idea of, if delta H is positive, as long as delta S is big enough to make it overcome the delta H, then yes, you will for sure get a negative delta G, and it will spontaneously dissolve. All right, Henry's law. You don't have to know the words Henry's law, but the idea here is that if you jack up the pressure of a gas, you increase the amount of that gas that will dissolve in the water. So if you want to carbonate a Coke, you jack up the pressure on it. And when you're doing that, you make all the little bubbles of that gas smaller, and smaller particles tend to dissolve better. So there are strong electrolytes and weak electrolytes, and sodium chloride is a strong electrolyte because it conducts a lot of electricity. And that's because it forms lots and lots of ions. When you pour salt into water, it forms sodium ions and chloride ions. That's called dissociation, meaning the ionic solid splits apart
into ions in water. Nitric acid, on the other hand, is not ionic, it's actually covalent, and it will separate into different ions and tear itself apart into hydrogen ions and nitrate ions. And so anything that's a strong acid is going to be a strong electrolyte. And any ionic solid that's really soluble is going to be a strong electrolyte, mainly because they just form lots of ions. Anything that's weak is something that when it dissolves, it does not like to dissociate, or it does not like to tear itself into ions. So vinegar is a very weak electrolyte. It does not tear itself into ions very much. And tap water has a little bit of stuff dissolved in it, but not very much. And then non-electrolytes are, of course, things that don't form ions at all. So I mentioned strong acids before. You just need to know a couple rules for strong acids. The strong acids are Hickel, Hibber, High, HCl, HBr, and HI. Those are your strong acids. And then nitric acid, sulfuric acid, and chloric acid, perchloric acid. The basic rule is anytime the oxygens outnumber the hydrogens by 2 or more, then it's a strong acid. But in AP Chem, you're going to see nitric acid, sulfuric acid, and then perchloric or chloric acid. Anything other than those strong acids has to be weak. So anything that is not a strong acid, Hickel, Hibber, High, nitric, sulfuric, has got to be weak. Bases, on the other hand, are all ionic compounds for the most part, the ones that are strong. So anything that's really soluble, the group 1 hydroxide, sodium, potassium, lithium, rubidium, those are all going to be strong bases because they're very soluble and make lots and lots of hydroxide ions. Weak bases are going to be the ones that don't ionize very much, and so ammonia is your big one. On AP, if it's a weak base and it's not ammonia, they'll tell you. Pyrimidine, a weak base, or something like that. They'll tell you it's a weak base. Now, in Chemistry 1, you were taught that there were 5 types of reactions. There was synthesis, decomposition, single replacement, double replacement, and combustion. Well, I'm here to tell you that that's a lie, because there are really only 3 kinds of reactions. There's precipitation reactions, where you make a precipitate. Now, you probably learned that as a double replacement reaction. And it is, but we call that one specific type of reaction, where you take ions that are in solution and they make a precipitate. Then there's acid-base reactions, and you probably learned that as another type of double replacement reaction. This is a neutralization, where the acid and the base basically wipe each other out. And when the acid and base mix, they always make a salt and water. So those are the 2 of the 3. And then the third one is something we call an oxidation reduction or redox reaction. And in an oxidation reduction reaction, that's when electrons are transferred. Somebody picks up some electrons, somebody loses electrons along the way. And that is synthesis, that is single replacement, that is decomposition, and that is combustion. So why did we lie to you in Chem 1? Well, in Chem 1, we just structured it differently so that you didn't feel overwhelmed by having this one type of reaction that's got all these different rules with it. So we split it up into several different subtypes of reactions. All right, you guys need to know these basic solubility rules. Chlorides are... Now then, when you guys took Chem 1, you were taught to write an equation like this, right? Well, an equation like this is okay. It's the molecular equation, pretending that everything is molecules, but this isn't actually true. If we wanted to make a reaction seem truthful, then what we could do is we could make a complete ionic equation. In other words, anything that makes ions, you really should show living as ions, not as together. So here's that same equation written as a complete ionic or full ionic equation. And notice all I did was split up anything that's ionic and that is soluble. The only thing I didn't split up was the silver chloride, because it's actually a solid on the bottom, so it wouldn't exist as ions floating in solution. To take it one step further, we could do this. we could make a net ionic equation. So in other words, we could take the things on the left and the right that are the same, and we could cross them out. They are called spectator ions. All right, so we will practice this a little bit in class, but I'll go back and show you a couple things. Here is the complete ionic equation one more time, and notice what is exactly the same left and right. Well, yeah, the sodium, and of course the nitrate. And so if we cross those out, we're left with that. And that's all net ionic equation is. All right, well, that should do it for podcast 4.1. So thank you for sticking around, and thank you for being a part of AP Chemistry, and I'll catch up with you later.